Today's lesson will be about uncertainty. Uncertainty is doubt in measurement. How much uncertain we are about a quantity that we have measured. Anything that we measure with any scale that we use or any instrument we use, it has a certain limit or certain accuracy limitations on it. Even the human that is measuring that thing uh, have different capabilities and different skill level. So there will always be some doubt, and that doubt or error will cause some uncertainty in the measurement. And physics is a kind of subject that does not put that uncertainty thing under the carpet and just say that, okay, this is the measurement. No, in physics, actually, uncertainty becomes more important in some cases than mm, the actual uh, quantity that we measure, because mm, the accuracy of the quantity can only be examined or judged on the basis of the knowledge of error. So not errors are very important in the measurement of the quantity. Now, errors have types, like some are absolute errors, then there are fractional error, and then there are percentage error. Now, let's start with absolute error. What is absolute error? Or instead of error, I should use term uncertainty. Absolute uncertainty. I should have done that with the others as well. So just 1 second. It's not that error is incorrect, but we will be doing another thing with the name of error, and sometimes students confuse themselves with one another. So we'll call it uncertainty. Uncertainty. Fractional uncertainty. Percentage uncertainty. What is absolute uncertainty? This is a type of uncertainty that has same unit as measured quantity, has only one significant figure. One significant figure. Error should have only one significant figure, has decimal positions that can be added or subtracted from quantity. Okay, it has a decimal position that can be added or subtracted from the quantity. Now, see, if we have a measured quantity like 4.32 plus minus 0.02 kg, okay, it has same unit as the quantity. So this is 4.32 kg, and this is also 0.02 kg. So they both have same unit. Secondly, there is only one significant figure in the uncertainty part. See, this is the only this is only one significant figure. Now, listen, if you go back to class 4 or class 5, where you started to add decimal numbers with one another, and if somebody asks you to add 2.3 plus 1.07, you cannot just 2.3 and 1.07. The proper way of adding is the decimals should be aligned, and you cannot add unless you assume there is a zero over here. And then you say it is 7, 3.3. So the 3.37 if we assume there is this zero. Otherwise, you cannot add these two numbers. And listen, this means when we adding or subtracting, there should be equal number of decimal positions after the decimal or before the decimal. Otherwise, we will not be able to add or subtract numbers. What I mean by before and after the decimal. For example, if we have one number like 4,729, okay, just make it 700, and plus minus 425. So this number is not in one significant figure. First, we have to round off to one significant figure. It will become 400 plus minus. Now, what is the decimal position of this one significant figure that is in the error? Is it one decimal place, two decimal place, unit, tens, hundreds, thousands, millions, trillions? What is the decimal position of this one significant figure we have over here? If you notice, it is hundreds, 400. So it means we have to round off this thing to the nearest hundred. So when we round off this thing to the nearest hundred, it will become 4700. So this is why in the last lecture I was rounding off everything very easily to a known or fixed number of significant figure in a particular manner. And I was able to do that because I knew that I have to round off the error to one significant figure, and to the quantity should be adjusted to the appropriate number of significant figures and decimal positions. Yeah. Let's do some practice for this one. I'm giving some raw answers and I want you to put them to the right way. Okay, these answers are not right. They are all incorrect, you have to correct them. 1, 2.3745 plus minus 0.2319. Okay. Just make it to the appropriate number of significant figures and everything should be fixed. Okay, this is your task. I'll be writing two more, or actually three more. You have to fix them. Okay. Now, this is another question. Okay. Now, here you go. Do you have these four questions and you have to uh, convert them to the proper answer? The rules are that the error should have only one significant figure and the quantity should have an appropriate number of decimal position that can be added or subtracted from the error or the uncertainty that we are calculating. So if you're watching this as a recording, you can just pause the video at this point, do it yourself, and then see what is happening. Okay. So the first one is this, and in order to make it one significant figure, it will become 0.2. And because it is one decimal place, we are supposed to round up the quantity in one decimal place. It becomes 12.4 because the number that we have to ignore is more than 5, hence the previous number increases by 1. In this case, again, we have a raw answer, which is like this, but we need the final answer. In order to get the final answer, first we round off the quantity, the uncertainty of the quantity to one significant figure. It becomes 0.6 zeros and 5. So it means this is the seventh position, seventh decimal position. I go to the quantity and look for the seventh decimal position. I find this 3 over there. So this is the point where I'm supposed to round off the quantity. And I do the same, 0.00033793, plus minus 0.605. In this case, I have to round up the quantity to one significant figure. So one significant figure, 441.793 will be 400. It means that when I go to the quantity and look for the rounding off, I have to round up this thing to the nearest 100. In order to do that, I have to look for the number that is at the position of hundreds. Is this one at the position of 100? No, it is unit. Is this 8? No, it is 10. This 3 is at the position of hundreds. So this is where I'm supposed to round off the quantity and it will become 7, 9. And the number next to this one is more than 5. So I round it off and it becomes 4. 79400 plus minus 400. The last one, when I make this one, the error go to one cent figure, it becomes 2 plus minus 174. Now, what happens to errors when they are like added and subtracted? Before doing that, let's discuss what are fraction errors. So this is all about absolute errors. Absolute error have one significant figure. They have the same unit as the quantity, and they should have decimal positions that can be that can agree with the quantity as well. Now, next thing on the list was fractional uncertainty. Fractional uncertainty. Okay. Uh, I'm. I ask you a question. Tell me, I was measuring something using any measuring instrument, and I made an error of 0.1 millimeter. It is 1/10 of a millimeter. How much? 0.1 millimeter. I was measuring something and I made an error of 0.1 millimeter. You know, the millimeter is the smallest division on your scale. When you look at the geometry box scale that you have in your geometry box, the smallest two lines, the daylight between them, the gap between them, or the space between them is exactly 1 millimeter long. Now, what do you think if I make an error of 0.1 millimeter? Is it a big error or a small error? Just 1 second. It is a trick question. We can never tell an error of 0.1 or 0.001 or 0.00000000001 is a big error or a small error unless we don't know what we were measuring. For example, if you were measuring wavelength of red light, then it is 0.00000007 meters. So in that case, making an error of 0.0000001 is still a very big error because you are measuring very small thing. And then in that case, the error will be very significant. But what if you're measuring height of your room? You have to put some wallpaper on a particular wall and you want to measure the height, and while measuring the height you made an error of 0.1 millimeter. Not a big deal. Believe me, if you made an error of 1 millimeter, it is not a big deal in measuring length of a room, unless you're building some particle accelerator kind of thing. In that case it might be, but if you're just measuring it for the wallpaper and you made an error of 0.1 millimeter, I should give you a, an award for that. But because that would be a very, very nice measurement. So fractional error comes in. Fractional error is a type of arrangement where we can compare the error that we made or the uncertainty that we have to the quantity that we measured. So it will tell us or give us a better understanding of how big an uncertainty is. So fractional error is ratio of absolute uncertainty and measured quantity is called fractional uncertainty. Now, we can write it like this as well. Fractional uncertainty equals to Absolute uncertainty divided by measured quantity. So, for example, we have 37.10 plus minus 0.02, 7.11 plus minus 0.02, 0.47 plus minus 0.02, 0.09 plus minus 0.02. Now, I hope you can see I made the same absolute error in all four measurements. These are four different things, and I have the same absolute error. Do I have the same fractional error in every case or not? Now, which one can you imagine? Which one of them, without even calculating, which one will have maximum fractional error? They all have the same absolute error. Which one will have maximum fractional error? I don't want you to calculate that for now, but I just want you to think which one does. So remember, fractional error is absolute error divided by measured quantity. If you have the same absolute error, same numerator, the one that is the denominator that will be the smallest will get you the maximum fraction. So answer should be the last one will have maximum fractional error, and the top one will have least fractional error. So let's calculate the fractional error of all four of them. Hurry up, calculate them, and then tell me what answer do you get. Now, just 1 second. Let me share the screen now. In order to find the fractional error, what we need to do is we divide the absolute error with the quantity measure. So first one will be 0.02 divided by 37.1, 0.00054, 0.0028, 0.426, and 0.222. And one more confusion that student get is that in case of fractional error, it is not mandatory to round it off to one significant figure. It should be two significant figures, and some cases the examiner won't mind if you put one extra significant figure over there, because it is fractional error, and fractional error has no uh, compulsion of having one significant figure. So these are the significant figures. In next lesson, we will be discussing how these fractional errors affect the calculations and how do we find fractional errors caused by multiple quantities in a single calculation. So till then, take care. Allah Hafiz.